So here's 5.1 problems. We have a weak acid. That's all you need to know. You know it is because it's not one of our strongs and it has a Ka value. And so we're going to add no KOH at first. And we're just going to have 0.12 molarity benzoic acid. So then what would it do? Well, we have acid and water. It would make some of the H plus and some of the conjugate base anion. We know it's going to destroy one of these and make one of these and one of those. You can write out an ice box if you like. I'm hoping by this point you can kind of do this in your head, because for speed on the real test, that's pretty much what's needed. If you need to, though, hit pause and draw one out. And these will be the products, and this will be the reactant. We'll take the original molarity and lose the unknown X amount, but Ka is still small enough compared to the molarities involved that we can cross out minus X. It won't change the 0.120 enough to matter. Solve for X, and X is the H plus, remember? So we can take negative log of that and get pH. So if we add a certain amount of KOH, then we need to find the moles of each. You cannot do it in molarity. You must do it in moles. Liters times molarity is moles. Now, if they're going to work with something 1,000 times smaller than liters, this is milliliters, then they're going to get 1,000 times smaller than moles is the answer. And this is millimoles, or this is 0.012 moles. So you can do it either way. This one gives us something that looks like an integer. If you want to use millimoles, that's fine. So 3 of this would use up 12 of that because one of these reacts with one of those. You can write out the equation if you like, but I hope it's kind of obvious now that one of these will grab that H, the acidic H, and create the basic anion and water. So 3 of these will rip up 3 of those and create 3 of that. And maybe you can do that without an icebox, but here's an example. So we'll end up with 9 of this and 3 of that. So this value is 3, this value is 9 in our Henderson-Hasselbalch equation. You could just do this in a Ka version 2. And the reason we can use milliliters here is because we're using millimoles, because you can multiply or divide a fraction up and down as long as you do the same to both the numerator and the denominator, because it's a ratio. So if you're going to multiply or divide both by the same amount, you get the same ratio. So this again is millimoles, and this is milliliters. So you could use moles per liter, of course, but then you would get the same answer. You'd still get this canceling out, and this would still be 1/3. So log of 1/3 plus negative log of that, and you get the pH is 3.71. In this case, we're going to use double the amount of the KOH. It's still the same molarity. We're going to use double the amount, which means instead of 3 millimoles, we're going to use 6 millimoles, and 6 of this will burn up 6 of that. Now we have none of this left again, but 6 of this and 6 of that. We have our standard buffer amounts. We have the half equivalence point. We have equal amounts of the acidic version, the weak acid, and the conjugate base. And the thing to really remember from this kind of problem is that at the half equivalence point, the halfway point, the pH equals the pKa, because this is 1, log of 1 is 0, and this whole thing disappears. I even had made a little note here. Log of 1 is 0 because what we're saying here is 10 to the what power will get you 1. These are the same questions. What's in the box? 0. So log of 1 is 0. Log of 1 is 0. This whole thing turns into 0, and we add 0. For D, we add 60 milliliters, which is double what we said last time. So instead of 6 millimoles of OH minus, we have 12 millimoles, which means that the OH minus uses up all the weak acid. So we have none of this left. We have converted all the weak acid into the conjugate base. Here's the anion. And so now we have 12 millimoles of this. Remember, this is gone. Let's disregard it at this point. It's gone, 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 and it can't react anymore. So now, once that happens, what we have is this in water. Well, let's write out the reaction. What would happen with this in water? we would have this in water, and it's a base. It would pull some H's off the water, creating the acid version, and then creating OH minus. So we can make an icebox for that. And with just some very simple math here, we know that our molarity is that. Remember, we can use millimoles over milliliters if we want, because we've divided both the top and the bottom by the same amount. So the ratio is true. It might look a little odd, but it is mathematically true. Or you could do 0.012 over 0.160 liters, it's the same thing. So here's our icebox. Our K will be true once we hit equilibrium. Once these values are true, K will be true. But now we have the base version. We have the base version of this acid in water. So I had to find Kb, which I will do by taking Kw over Ka. And that will be equal to products over reactants to the power of the number in front. This is very small. This minus x will not matter at all. I solve for x, but what is x? X is OH minus. So negative log of that answer will give me POH, and 14 minus that will give me pH. On E, we're going to stop having the base be the limiting reactant, although the last problem had them both run out at the same time. And we're going to have the acid be the limiting reactant. So instead, this is going to be the greatest amount of moles, millimoles. And so this is going to run out, and we're going to have some OH minus left over. Now all these convert into that, so we have both of these. However, this we demonstrated has a Kb that is in the 10 to the minus 10 range, and is just worthless compared to this. Let's ignore this as immaterial to calculating the pH. So if we forget that, look, we have a millimoles in a certain milliliters of solution, and then we can get a molarity. Negative log of that answer is that, and pH is that. Now, if we sketch our previous 5 answers now, we get dot, 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 dot. This was the half equivalence point, right? If this must be the equivalence point, because this is where the pH hits effectively 7, right? So 60 milliliters, and we look, they both ran out together. That was the equivalence point at 60 milliliters of base used. So this must be the half equivalence point at 30 milliliters used. Now, I don't think the real test asks you to sketch it anymore, but it is very good to learn to do that. Plus, as a preparation for a college class, I would greatly recommend that you take a good look at this, and of course it's going to come up with more later, but sketching this with a straight line is not what happens. These things flow in curves because it's a real life progression, right? And also, though, it is tempting then to just say, oh, it does this, and look, I curved it, and that's just not what happens. So please recognize that it gets really close and takes a vertical. I don't think anybody's going to argue with exactly where it curves and exactly how vertical it gets, but my penciled line here, like something like that, is definitely wrong. And number 2, we're going to turn things around and titrate a base with an acid, except again, like previously in part A, nothing has been added, no acid has been added. I'll point out that this is a base because we have N, and it has 3 covalent bonds. It has 1 and then H and then H, so to speak. So it has 1 unbonded pair that it could donate as a bonding pair to an H plus coming in. And that is something that in general you're expected to recognize. It won't come up in this problem, but in general, there could be a problem where they expect you to know that that is a bonding site for another H plus, or at least something else. So this is a base. It has, again, a valence pair unbonded here on the end because it only has 3 covalent bonds and it has room for a 4th. And so it's going to grab one of the H's off the water, which is why we get OH minus here, and then we get H3 here instead of 2, and it's positive now because it grabbed an H plus. So you can write out an icebox if you like, but I'm hoping you can kind of do it in your head. Some of this is going to get destroyed, also making equal amounts of this and this that equal to the amount that got destroyed. So we get X and X. And here's our K expression. We got the K from up here, double checking, it is a KB. This is a base expression, so that does work. We're going to be able to cross this out because this KB is much smaller than that molarity involved. We solve for OH minus. Negative log of that number is POH, and 14 minus that answer is pH. So we're going to add some acids. So we got to find out the moles, and we can take milliliters times molarity if we're willing to acknowledge and write down that this is millimoles. Keep track that that's millimoles though. So we have our starting millimoles and millimoles. Half of this is going to burn up half of that. So we get this and 6 and 6. We have equivalent moles in the same solution. That is the halfway point, or the half equivalence point. Now that confused me, and I have said this before, but the reason is the half equivalence point is because we added this amount that was halfway to getting these to be equal, because it's not the fact that these are equal. When we were adding this to that, we added an amount that is half of that. If I added 12 millimoles, I would be at the equivalence point, and that's what's going to happen in letter D. So I added half the amount that would be equivalent, and that's why it's the half equivalence point, or the halfway point. So here, the problem solvers do something a little bit tricky. I'm going to show you another way we could do it too. They use the reverse version of the Henderson-Hasselbalch equation, where you don't have pH, you have POH. Now, if you're going to put POH, you need to use KB, and that's why they've done it, because they know KB. And if they want to use KB, then they have to put it into the POH version, which I will point this out, also flips this fraction upside down, and the acid version is on the top. This is the acid version, this is the conjugate base. Now, it's not necessary, but it is one way to do it. And so they take negative log of KB. They know this turns into 0 because it's the fraction is 1 and log of 1 is 0, and POH equals this, and then they can subtract that out of 14 and get pH. Now, that's a bit tricky, and that is kind of showing off in a certain sense. And I backed up and did this myself. If I use the standard version of the Henderson-Hasselbalch equation, I know this turns into 0, and pH will be Ka. So what is Ka? Well, Ka is Kw over Kb, which is this, and you can do that in your head because this turns into E negative 8, and 1 over 3 is 0.333. And I know that's not in standard form, but it doesn't matter. It's still a true fact. Negative log of that will be pKa, and that is pH, and look, we got the same thing.